Okay. Now, it is wise to give a comprehensive idea of the different points of view which are possible in developing a field theory, to talk a little bit about what can be regarded a dead end street, or using a French expression, a cul-de-sac for continuum mechanics, which actually became the way which opened our knowledge in a new field, which is tensor calculus. So actually, of course, this is my interpretation. Cauchy-Poisson did not appreciate and or understood the arguments by Lagrange and Piola. So they decided to base the postulation of mechanics starting from another point of view. I believe that I can show you that this way of proceeding is possible only if you have developed already a Lagrangian approach. Because there are so many arbitrary choices that if you do not already know the right answer to many questions, you cannot proceed. But of course, this is not my. This is simply my personal opinion. I hope to persuade you on this. This is one first statement. There is also another statement I would like to begin to tell you, then we will go in more details in this. When introducing the concept of balance laws, already in mechanics, instead of postulating one basic principle, you need to postulate at least three. And I do not want to go very far, but of course we could track the Occam principle of least thought. I mean, the Occam principle of the minimum of assumptions to be used for founding a theory in earlier studies. But the razor of Occam is always telling us that even if admit that two postulations are equivalent, and in my opinion this is not the case, but even if they are completely equivalent, you must always prefer the one based on the least number of assumptions. So for an economy of thought, I think that the dead end street which Cauchy started to use in continuum mechanics, it has been very misleading very often. However, the reasonings of Cauchy showed us the first linear map in a vector space into itself. And we can say that the first tensor was met by Cauchy. So in his reasonings, he needed to introduce a tensorial quantity, a tensor field, and he recognized the tensorial nature of this field, and he opened a series of interesting investigations in this context. Okay, so what we have to say that from the mechanical point of view, if you want to generalize a model, if you want to find a more careful, more detailed model for describing a class of phenomena, most likely the approach I am quickly describing for you is not the most appropriate one. However, historically, there is the famous tetrahedron argument by Cauchy, which deserves to be discussed. There is also another reason for which you need to learn about this point of view. Of course, my point of view is not unanimously accepted. So it is honest to let you know that there are different points of view. Okay. So what they are doing? They are considering a given body in the Eulerian reference configuration. Then they are considering a subbody P, which is a subset of material particles. The subset of material particles which in the given Eulerian reference occupy the points which belong to P. Then you must assume that there is a quantity small psi. There is a flux of this quantity, call it capital psi, and there is a source of this quantity, call it phi. Then you must postulate, with some painful Reynolds theorems, the balance of this quantity for every subbody, for every time instant. You have to assume that the integral over the subbody P of psi dot, where this psi dot, of course you can define it directly in this way. Where v is the velocity at which the quantity psi is traveling. Of course, you are adding not well-defined ingredients. Of course, you need to assume that there is a reference configuration, there is a mapping which is placing every material particle in the Eulerian configuration in order to be able to talk about this V. Okay? But anyway, you assume that there is this transport. You assume that the integral over P of psi dot integrated in the volume plus the integral on the boundary of P of the flux of this quantity plus the integral over P of the source of this quantity has to be equal to 0. This is a balance law. Of course, if you think what we have done with least action principle and Piola-Lagrange approach to continuum mechanics, at the end, when we have written the least action principle, then we have transported the minimizing partial differential equations from the reference configuration to the Eulerian configuration using the Piola transport. At the end, you get a balance where if you are talking about placement and forces and mass density, and if you are talking about the action we have introduced in the previous lectures, psi dot is the material derivative of momentum. If you are talking about force, psi is the flux of force, and phi is the external source of force. By the way, psi and phi and psi can be scalar or can be tensorial quantities. Okay. So in general you can have the balance of mass, which is a scalar, of energy, which is a scalar, of angular momentum, which is a skew-symmetric tensor. You can have the balance of many things. But in the general setting, you have this balance equation. Of course, in the papers of Cauchy and Poisson, there was no such a general setting in formulas. When they talk, when they write discussion about the formulas, they have more or less this rather general idea. Okay, now let us focus a little bit on this psi. Consider that in our variational setting, there is a unique Lagrangian behind psi, capital psi, and eventually phi. So these three fields you get in terms of one field, which is the Lagrangian. So you should already start considering that you could have troubles in dealing with this in the general setting, because you miss some relationships among these quantities. But this is also a very controversial point. So I try not to be so biased, so to tell you the story as it is. Okay. So what happens is that you assume that there is a field. This field depends on the point where you are estimating it and on the shape of the surface through which you are considering the flux of your quantity. So this psi is a function depending on points and sets. Because when you have this surface, in a given point of the boundary of the body, of the subbody P, of the part P you are considering, in general, in principle, you can imagine that the flux of your quantity not only depends on your point, but it also depends on the shape of this surface. So, for instance, you can imagine that if you have two surfaces in a given point, the flux estimated in the point which is in common between the two surfaces not only depends on the point where you are, but also it must depend on the shape of the cutting surface. Okay? This is a very crucial point. I don't believe, but I could be wrong, I don't believe there is any trace of the discussion which occurred between Piola and Cauchy about this subject. However, we know exactly what Cauchy thought and what Cauchy wrote, answering, unfortunately in Italian, answering to the choice of Cauchy, which I will tell you shortly. Okay, so in general, and this was clear in the mind of Cauchy, this field depends also on the shape of the cutting surface. Very often one thinks about so-called Cauchy cut principle, which is very abstract. I don't know why engineers consider variational principles very abstract, and the concept of Cauchy cut very practical. Think what Cauchy is assuming. He assumes to have isolated a body, a subbody P, and he thinks to remove the remaining part of the body, and he assumes that the action of the remaining part of the body on the part of the body of the removed part of the body, so on what we have erased, on the part which we are considering, he assumes that this action can be described in terms of such a field, which is the contact interaction field, a la Cauchy. Okay? So, for instance, if you have a fluid, you need to imagine to isolate a part of this fluid from all the surrounding part of the fluid. You remove the surrounding part of the fluid and you have to introduce, for instance, if you are considering balance of force, the force acted on the surface of your imaginary cut, force acted by the removed part of the fluid. Okay? Maybe with fluids this is even conceivable, but think about a beam, and think to perform a Cauchy cut of the beam, and to apply on this open now outcoming surface of the beam a set of actions, forces per unit area which are acted on that face. Okay, this is very, very artificial in every sense. I do not know why the concept of flux of force is considered more physical or more engineering than deformations and energy. I think it is only a psychological and or cultural story. It is a question of habits. Cauchy was in propaganda more effective than the Lagrangian group. So his ideas were more widely spread. However, you have a difficulty, very strong difficulty. Which is this difficulty? How to represent this flux? Of course, if you have performed the integration by parts, which I have shown you, starting from a least action principle, you know already that the shape of the surface of the Cauchy cut is intervening only via the normal vector, the normal unit vector to your surface. If your deformation energy is the particular deformation energy which we have studied. So if your deformation energy is a first gradient deformation energy. So if somebody already told you that the dependence of psi on this form is explicit only via the normal of this Cauchy cut, then following Cauchy, you can add to your treatment a suitable ad hoc assumption, which was called in a very misleading way, it was called a Cauchy postulate. I strongly believe that this assumption is a constitutive assumption, in the sense that for some continua, when considering a class of phenomena this assumption is acceptable, and for some other continua, this assumption is not acceptable. So assuming that this flux depends only on the normal of Cauchy cut is simply a constitutive assumption, an assumption which is talking about the particular nature of the body you are dealing with. So to call it a postulate is very misleading, because you should reserve the word postulate only for balance of energy, conservation of mass, least action principle. You shouldn't use postulate for specifying a particular property of a particular class of materials. The straitjacket which is impinging the movements of the minds of many persons is a straitjacket which is based on this misunderstanding. Because people believe that every material, every continuum must have a contact interaction of the Cauchy form, because this is a postulate. I mean, this is a fundamental physical truth. Fundamental physical truth which was questioned in a very polemical way in 5 lines of the work of Viola in 1848, where he proves that this assumption he is able to remove. Okay, he is able to remove this assumption. Okay, but let us accept it. So, if you have 2 Cauchy cuts which are tangent in a given point, then you assume that the flux per unit area of your quantity in that point depends only on the normal of the 2 surfaces you are considering. Which means, in other words, that the 2 tangent surfaces, sigma 1 and sigma 2, here in the point of tangency, in that point, they see exactly the same flux. I repeat you, of course, if you know, having seen the integration by parts, that this flux depends only on the normal, because you apply divergence theorem and you get here the flux of something, then you are powerful, you have a very powerful force which pushes you to make this assumption, which otherwise is very unnatural in a sense. After having accepted this assumption, Poisson and Cauchy start talking about that the interaction between the plus side of your body, so the one in which the normal n is pointing, and the minus sign of your body depends on the interactions between molecules which are trapped in a given ball having as a center your point. Of course, if you change the surface keeping the same tangent, okay, this part and this part one time belong to the plus side, the other time belong to the minus side. So the interaction between these 2 sides of these 2 bodies, when you consider 2 different Cauchy cuts, is an interaction between different groups of molecules. So there is no reason for which it should be the same. With an argument based on a limit, with a sentence which can be formulated in this way: sensible actions are occurring only at insensible distances. Okay, which is rather difficult to prove in any, and indeed it has been proven only in very recent papers with the techniques of homogenization and gamma convergence. Okay. Anyway, the idea is that this radius can be taken so small that the difference between the two groups of molecules which are interacting is very small. So that this psi, instead of depending on the shape of the boundary of P, can be assumed to depend only on the normal of the boundary of P in a given point. Okay. But when you apply Gauss theorem and you get an integration by parts, and from bulk divergence you get boundary conditions as we did previously, the dependence on the normal n is a particular one. This dependence is linear. So now Cauchy understood that for proceeding he strongly needed to get that this dependence is linear. Okay? So we are now ready to draft. I hope that you have heard about it. Of course, I have read many books and I've discussed with many persons. There are persons for which linear dependence and general dependence are the same thing. So I have seen many persons who do not feel the need of proving any theorem. They simply claim that if NA is the component of N, let us introduce small letters because this is Lagrange, then the flux can be represented with the normal is a covector, the flux is a vector. So you get the saturation between the components of the flux vector and the components of the normal vector, and you have done everything. Of course, this T may have many other indices, but you simply need one saturation. So you can forget about the other indices. In this context, we are talking about a scalar quantity and a vector quantity for its flux. There is no loss of generality because you are saturating only the normal. Okay. So this is a very, very delicate point. You should consider that depending in a linear way is not the same thing than depending on your vector quantity in a generic way. So Cauchy was aware that he needed an argument for proving this dependence, this linear dependence. Okay. So, if you have a quantity which depends on the normal of your Cauchy cut, your powerful tool, very powerful tool, is that you know that the upper bound of this quantity, of course we have to consider what we mean with this norm, because this is a tensorial quantity. So let us start with a scalar, then you don't have problems. So Tn if a scalar, so this is a real number, you have done it. When you assume that this flux is balanced, with a source and with a time derivative of the same quantity, as we have written before in the equation which I have erased, then you can say that this surface integral is upper bounded by a constant quantity times which does not depend on anything. I mean, it depends on, once you have fixed your fields, this quantity is fixed, okay? Times the volume of the body, of the subbody P you are considering. Okay. Indeed, this is a theorem due to null, which has been, to my knowledge, has been proven by null, but it is a simple application of measure theory. Actually, if you have a field which depends on the shape of the surface, remark, this flux is a density per unit area. This is a crucial assumption of null theorem. So if you have a Cauchy cut and the flux of your quantity at your Cauchy cut depends only on a field which integrated with respect to the surface measure. So if you have a density of flux per unit area, in other words, you don't have fluxes concentrated on edges. You don't have fluxes concentrated on points. So you don't have any positive flux concentrated in parts of the boundary whose area is 0. This can be said in a very complicated way using measure theory. If the flux is absolutely continuous with respect to the Hausdorff measure 2. So if, in other words, which are more understandable, if you have a small area, the flux is small, and when the area tends to 0, the flux tends to 0. Okay? So you don't have for instance, fluxes concentrated on edges and on points, this point will be crucial. Okay. Then what null is proving is that the dependence on the surface reduces to Cauchy assumption. So actually, Cauchy postulate can be mathematically relaxed. You have a body, you have balance of something, you have flux of this something you are balancing. Okay? Don't believe that this proof or this argument is complicated. It is very, you need patience. You need a series of upper bounds for proving it. There is nothing complex. So if you have the balance of something and the quantity you are balancing has a source which is volumic, a time variation which is volumic, and a flux which is concentrated on a surface, and this flux do not is not non-vanishing on parts of the surface having area 0. So when the area is 0, a part of area 0 sees only 0 fluxes. Okay, so this is a simple surface integral. Then the Cauchy, so-called Cauchy postulate is automatically true. If you will be patient, I will show you the equations of a capillary fluid. For capillary fluids, the flux of force depends also on the curvature of the Cauchy cut. So it doesn't depend only on the normal, it also depends on the gradient of the normal. Okay? Then one could believe that, if you believe that this is a general theorem, you are lost. You claim that these capillary fluids cannot exist. You have to know that the theorem of null is true simply because he assumes that flux on the boundary is vanishing in every sub-part of the boundary, of every surface at the boundary, which has area equal to 0. So in other words, you must expect that capillary fluids have contact actions which may be concentrated on edges. So you have forces per unit line, not only forces per unit area when you perform a Cauchy cut. So again, if you believe in your model blindly, you may risk to behave as Pythagoreans who claimed that the hypotenuse of a rectangular triangle is not existing, simply because square root of 2 is not a number. You need to add an adjective. It is not a rational number. So you can prove, if in your mind the concept of number is confused with the concept of rational number, then there is no such triangle with 1, 1 and square root of 2. Of course, the clever point of view is to say, okay, then there are other numbers. Rational numbers are not enough. Or if you prefer, the mathematical model given by rational numbers is not sufficient to model every quantity. So you need real numbers for modeling quantities. Okay? Now here in our small, not so important situation, we are facing a similar circumstance. If you want that fluxes are absolutely continuous with respect to the area of contact surface, then the flux depends only on the normal, and I will prove you using tetrahedron argument, they depend linearly on the normal. These ideas are so deeply rooted in the head of many human beings that they cannot conceive any material which is not respecting this assumption. And this is the big problem one meets when he tries to generalize this treatment, because people at worst tell you that all this is a mathematical useless game. The most clever people tell you that contact interactions are sensible only at insensible distances. Which is not true. Because if you consider a drop of water in equilibrium with its vapor, you know, everybody accepts that the jump of pressure depends on surface tension and radius of the drop. Okay? But if we have written the Euler equations for a fluid, gradient of P in absence of inertia and bulk forces is 0. So how you can get constant pressure and jumping pressure? You have two possibilities. Either you say that drops and vapor are not one material and you have a bidimensional surface, a physically bidimensional surface, which is dividing the two faces. So you need to introduce a theory of a three-dimensional continuum inside, a bidimensional continuum on the surface, and another three-dimensional continuum outside, with terrible difficulties, because one material particle of fluid, of water, when it wants to become vapor, it has a starting volume which is non-vanishing. Then it shrinks to enter the surface to a material particle with 0 volume. Then it expands another time to become a volume. So phase transition becomes a nightmare modeling phase transition. Or you go to the good sources, Piola, and you discover that when you can have sensible contact actions at sensible distances, then Cauchy assumption is not valid anymore. So to relax Cauchy assumption, what you have to do? You have to assume that flux depends on the shape and that it is not absolutely continuous with respect to area. So you can have non-vanishing fluxes in areas which are vanishing. Okay, so this is for making clear, because very often I heard this objection. What you are telling us, null theorem is true. So read null theorem instead of hearing. Every theorem is based on hypothesis. The assumption of null theorem is flux is expressed in terms of integral over a surface. The integral over a vanishing surface is 0. So this flux is absolutely continuous with respect to area. Okay, so let us proceed slowly. I will draft the clever argument of Cauchy. So even if this argument can be repeated for every tensor quantity, let us talk about stress. So force is the balanced quantity. The argument holds in general. Okay, so the clever idea of Cauchy is to consider a tetrahedron. So he chooses E1, E2, and E3, 3 unit vectors, orthonormal. So each one has a length equal to 1, and each one is, every pair of these is orthogonal. Okay? So the trick which is in the head of Cauchy is old, which is the volume having as boundaries planar faces whose number of faces is minimum. This is the geometric property which is the basis of our argument. So somebody should explain me why basing mechanics on Cauchy argument is easier than basing it on Piola's argument. Now you have to think about very complicated properties of three-dimensional Euclidean space. So take a normal. I have some difficulties in drawing, so I try to draw the simplest possible drawing. So you consider a triangle whose vertices belong respectively to E1, E2, and E3 straight lines. Okay? Then you assume that the normal n is normal to this triangle, and you keep this normal constant. Then you consider the vertex, the origin of your orthonormal system, as a vertex of a tetrahedron whose triangular faces are the triangle which you have used normal to n for finding these 3 points. Then you have this triangle whose normal is E3. Then you have this triangle whose normal is E2. And then you have this other triangle whose normal is E1. Okay? Then you call epsilon a very small number, a positive number, not very small. Then you will manipulate it as you like. You call epsilon the distance between the origin of your coordinate system and your base triangle, the one you have defined. So if you call this P1, P2, P3, your tetrahedron is the tetrahedron of vertices origin P1, P2, P3. The triangle P1, P2, P3 is orthogonal to N. And then you have one triangle O, P2, P3, whose normal is E1, and so on. Okay? So you have completely characterized your tetrahedron, which is a closed volume whose faces are planar, and the number of faces is exactly 4. Consider that the dimension of the vector space we are considering is 3. So if you have a vector in this space, you can represent it as a linear combination of 3 bases, 3 vectors belonging to the bases. And in particular, we have E1, E2, and E3 as this. Okay, then let us proceed a little bit. If I have the normal n, which is a unit vector, I hope that you remember that this vector is represented in a unique way as a linear combination of EI's, and that these coefficients, alpha I, are given by n inner product EI. So the components of a vector in an orthonormal basis are given by the inner product of the vector with the vector of the basis. So here we can write n dot EI EI. So you can see you have all complicated ingredients you believe that you are avoiding. The question is that you are drawing pictures, so you believe it is easier. Then you can have this very clever idea. You can call Fn the triangle having normal n, face n. Then you can call F1, F2, and F3 the triangles having normals respectively E1, E2, and E3. And then you need an information which is available in books of solid geometry, which has been studied since the times of Euclides and were considered a fundamental part of every curriculum for high school. I remember I studied this at the 3rd year of a classical school, which was the last one. If in the Italian convention is the 5th year, is the 3rd liceo. Okay, which is this property? The area of Fn times N inner product EI equal the area of Fi. If you like, the shadow of the triangle P1, P2, and P3 on the plane E1, E2 is exactly the triangle F3, and this shadow is the cosinus between N and the normal E3. There is this ancient rule which comes from Optica of Euclides. If you have two surfaces and you are projecting one on the other, then the ratio of area is equal to the cosinus of the angle between the normals. Okay? This was conceived by Greek scientists for building lenses, because they could produce corrective lenses. Okay? Now, this tells us a very important property among all these areas. The tetrahedron, I will call it Tn epsilon. The whole volume, I could here calculate the volume of this animal, but this is absolutely useless for our aims. Why? Because when epsilon is small, anyway, this is always true, this volume is proportional to the cube of epsilon. So actually, you have this property. Remark that now I can consider a family of subbodies. I have my fluid. I've seen many of these pictures because, you know, books of science are copied one from the other. Sometimes you don't know. This is typical of copyists. You do not know why there is a picture in a book. There is no description about Cauchy Theorem, but you see a tetrahedron with this geometry with epsilon which tends to 0. One reads and says, why? The author was copying a more ancient source, and he was deciding against Gramsci's opinion that some simplifications were needed. So he decided to assume that flux of force depends linearly on the normal of the Cauchy cut. However, when describing physically with words Cauchy cut and the fact that Tn direction n is the traction or compression, and in the tangent plane of Cauchy cut it is a shear contact force, then they use the picture of their source. And either they write a cube or they write a tetrahedron, because both of them can be used for such an argument. Okay? I want to underline that soon we will assume for the epsilon family of bodies, all these tetrahedra. So you have a one parameter family of bodies with epsilon tending to 0. You assume that balance of force holds for this family of bodies. So what you assume? You assume I have a body. I have a point of the body. And for every subbody, the balance of my quantity holds. Because every subbody is a system, physical system by itself, and for him, the balance of my quantity must be valid. Of course, what is the external world for every of these such bodies, subbodies, for every such subbodies? It depends on the subbody. So if you consider a smaller epsilon, then contact action changes, because you have different Cauchy cuts as a surfaces. Okay? So this is the point. So you consider a one parameter family of subbodies, and you assume the balance of force for each of these subbodies. So you will write an equation which is valid for every epsilon, and then you will use Cauchy definition of limit, some theorems about integrations, and you will get an interesting result. But before proceeding, I will conclude this theorem next lecture, so I am preparing all ingredients for this. Or maybe we have time, we will see. I must warn you, the mean value theorem is not valid for vector quantities. You have to understand this, otherwise you are lost. I have seen many people applying the mean value theorem for, I will not tell the main character of this story, but I had a PhD student who believes to be very clever, and one day he decided to prove a very clever theorem whose basis was the following. He applied for a vector field mean value theorem. And of course he was complaining that I was an old and senile person nearly outside the reality, because I wanted to stick to mathematical details of a more complicated theorem. Actually, his result was absolutely wrong. It has been published. So my opinion has not been considered, but that result is absolutely wrong. So let us think about this. You know, you are young and you want to become researchers. So you need to learn that mathematics is not a game of symbols on a blackboard, and you are clever like you know that Neapolitan person playing with 3 cards, and you must discover where the king is, and they move the cards quickly, and you bet, and of course you lose the majority of times. Okay? Mathematics is not that game of 3 cards. You must follow some rules for keeping a value of truth to your statements. So you need a chain of correct deductions for arriving to a true statement. So everybody has studied that if you have a continuous function defined in an interval, the integral of this continuous function in your integral can be represented as the value which is assumed somewhere by your function, the mean value, times the length of the interval of definition. So in a sense, of course, my drawing is not perfect, it's not correct even, so you need a bigger, maybe this one, no, even not this one. You need this one, something like that. This area is equivalent to the other area. Okay? So, in general, the Xi may be more than one. Your theorem tells you that there exists such a Xi. And many engineering students believe that this is the typical theorem conceived for not allowing them to become engineers, because it is a theorem which is taught the first year. Actually, my generation learned it in high school, but it is learned in calculus first year, and it is considered another useless because trivial theorem. Of course, if your function is not continuous, the mean value is not the value of a function, of the function. It can happen something like that. So you need a strong assumption. You need a continuous function defined in an interval, and then you can write, by the way, this is a Lagrange theorem, integral between a and b of f of xi dxi equal f of x bar suitable one times b minus a. This representation formula for the integral is so-called mean value theorem. You should never believe it is true for functions which are not verifying the assumptions of your theorem. Could also happen that you don't have the function defined in an interval. If you have the function defined in two intervals which are disjoint, then you are in trouble. But what is very delicate, and we need to understand it if we want to understand Cauchy theorem, is the following. Life is like that. Examples, counter-examples, theorems. If you try to prove a theorem and you don't manage to prove it, then you should start proving counter-examples. So you need to find some examples in which the hypotheses of the theorem are verified and the thesis is not. Okay. So I propose you call it this E1 and you call this E2. By the way, all this is written in all details in my book with Bishara. Then you divide your square into triangles. In this point, you define a vector parallel to E1. In every point of the other triangle, you define a vector parallel to E2, and the length of these two are equal to the distance of the application point with the diagonal. So you have to close your eyes, and you can do it with Mathematica easily, or you can play with this function very easily. So you have a set of arrows. In the upper triangle, these arrows are pointing parallel to E2. In the lower triangle, the arrows are pointing parallel to E1, and in every point the field, because this is a vector field you are defining, the vector field you are defining is such that the length of your arrow is equal to the distance of the application point with the diagonal. You can easily check that this field is continuous, because when you go close to the diagonal, they tend to 0. I don't need to prove to you that the integral of this vector field is lambda times E1 plus E2. It is symmetric, okay? And that this lambda is non-vanishing. Try to apply here the mean theorem, the theorem of the mean value theorem for integrals. There is no point in your domain in which your field V has the direction of your integral. So the mean value theorem is not applicable to vector fields. It is not true. Now, before ending, why we are so interested to mean value theorem for vector fields defined on surfaces, in particular on triangles. When considering our tetrahedron, consider the face Fn. You can introduce the so-called Cauchy vector field Tn, which is the vector field defined on the face Fn, which integrated over the area gives you the resultant of contact actions on the face Fn. This is an integral per unit area, and Tn is a vector field. Okay? You do not know that T linearly depends on n. You will prove this. So I call, using the tradition, Tn the Cauchy vector field. Okay, this is the force per unit area applied by the part of the body outside the face Fn, so in the direction of outward pointing n, okay, on the inner part of the surface. Okay. Then I can add sum over I equal 1 to 3 of integral of Fi of T minus Ei, the area so this is why I'm introducing E minus Ei, because the outward pointing normal is minus Ei, because the body we are considering is the tetrahedron, and these arrows are pointing outwards. This is plus integral of inertia plus bulk forces B over the volume T n. Of Of course, you have everywhere epsilon. And all this is equal to 0. So I will show you all details of this deduction in the next lecture. But I want to tell you why we need a mean value theorem, which is the idea of Cauchy, which is not so stupid. This goes with epsilon cube. This goes with epsilon square. So if I divide everything 1 over epsilon square, this goes to 0, and this goes to a finite number. And this finite number will allow me to represent Tn as a function of T minus EI. So, even if I am against Cauchy in many aspects, I must admit that this argument is very clever. Of course, Cauchy was very well known to understand other people's work and publish it, so we can never say what happens. But this argument is very clever. But for proceeding, I need to represent this integral how? Area times the value of t somewhere. But this argument is not true. Mean value theorem is not true for vector fields. So once I write balance of force in this way, I still am in troubles. And here you discover that Cauchy knew about Piola argument. Out of the blue, he calculates the power expended by these forces on a translational motion. So he calculates the inner product of this animal times a generic vector V0, constant, which means I am virtually translating V0 with the velocity field V0, this tetrahedron. Okay? By the way, in many Italian books, when you write balance of forces for Cauchy continua, they call it balance for translations or translational balance. And the reason is clear. Okay, so before stopping, remember for next Tuesday, because we will complete this argument next Tuesday. Once you have the inner product of integral times a constant vector V0, the vector V0 can go inside all integrals. So you have B inner product V0, T inner product V0, T inner product V0. And now you are Lagrangian. You are calculating integrals of scalar quantities. The average theorem for integrals holds. Okay? Okay, so we will complete this argument next Tuesday. Okay?